Beyond the familiar planets that orbit our Sun, beyond Mars and Jupiter and the ice giants at the edge of our solar neighborhood, there exist worlds we can barely imagine. More than 6,000 of them have been confirmed. Planets circling other stars. Some larger than anything in our system, others smaller than Mercury. Rocky worlds and gas giants, scorched planets and frozen spheres, realms of endless night and perpetual twilight. The number 6,000 feels substantial when you consider that the first of these distant worlds was confirmed only in 1995. 3 decades. That's all it took to go from wondering if planets existed around other stars to cataloging thousands of them. The confirmation came on a clear autumn day in October, when astronomers Michel Mayor and Didier Queloz announced they had detected a planet orbiting the star 51 Pegasi, located approximately 50 light-years from Earth in the constellation Pegasus. But 6,000 confirmed, exoplanets represents only the smallest fraction of what exists. Statistical analyses of data from NASA's Kepler Space Telescope suggest our galaxy contains more planets than stars. With somewhere between 100 billion and 400 billion stars in the Milky Way, that implies hundreds of billions of planets, perhaps even trillions. Most remain hidden, waiting. Their light too faint, their effects on their parent stars too subtle for our current instruments to detect. Consider that number for a moment without urgency. Hundreds of billions of planets. Some orbit stars so similar to our Sun that, if you could stand on their surfaces and look up, the daylight might feel familiar. Others circle red dwarfs, stars so cool and dim that their planets must huddle close just to stay warm, completing entire years in a matter of days. Still others drift alone through interstellar space, untethered to any star at all, moving through darkness that our Sun's light will never reach. The revelation that planets are common, perhaps even ubiquitous, changes our understanding of the cosmos in ways that are difficult to overstate. For most of human history, the question of whether planets existed beyond our solar system remained purely philosophical. We could observe stars, we could measure their distances and categorize their colors and spectra, but we had no way to know if they hosted worlds of their own. The discovery of the first exoplanet around a Sun-like star in 1995 didn't just add one more object to the astronomical catalog. It opened an entirely new chapter in our exploration of the universe. That first confirmed planet, 51 Pegasi b, turned out to be nothing like astronomers expected. With a mass about half that of Jupiter, it orbited its star every 4.2 days at a distance of just over 7 million kilometers. For context, Mercury, the innermost planet in our solar system, orbits the Sun at a distance of approximately 57 million kilometers and takes 88 days to complete one revolution. This new planet was closer to its star than Mercury is to our Sun by a factor of nearly 8, completing an orbit in less than a 20th of the time. The existence of such a planet challenged prevailing theories of how planetary systems form. Scientists had assumed that gas giants like Jupiter could only form far from their parent stars, beyond what's called the frost line, where temperatures are low enough for volatile compounds like water and methane to freeze into solid ice. These ices could then clump together to form the cores of giant planets, which would subsequently accumulate massive envelopes of hydrogen and helium gas. A Jupiter-mass planet orbiting so close to its star seemed impossible according to this model. Yet there it was. Real. Observed. Confirmed through multiple independent measurements. The discovery forced astronomers to reconsider their understanding of planetary formation and evolution. Perhaps giant planets could form far out and then migrate inward through interactions with the disk of gas and dust surrounding young stars. Perhaps the dynamics of planetary system formation were far more complex and varied than anyone had imagined. The years following that initial discovery brought a steady stream of new exoplanets, each adding another piece to an increasingly intricate puzzle. By 2000, astronomers had confirmed the existence of approximately 30 exoplanets. By 2010, that number had grown to more than 400. The launch of NASA's Kepler Space Telescope in March 2009 accelerated the pace of discovery dramatically. Kepler operated on a beautifully simple principle. It stared continuously at a single patch of sky containing about 150,000 stars, watching for the slight dimming that occurs when a planet passes in front of its star from our perspective. This transit method required patience and precision. The dimming is tiny. When an Earth-sized planet transits a Sun-sized star, the star's brightness decreases by about 80 parts per million, or 0.008%. Detecting such subtle changes demanded instruments of extraordinary sensitivity and stability. Over 9 years of operation, Kepler discovered more than 2,700 confirmed planets and identified thousands more candidates awaiting verification. The mission revealed that small planets, those between the size of Earth and Neptune, are remarkably common. Statistical analysis of Kepler data suggests that about 20 to 50% of Sun-like stars have rocky planets in or near the habitable zone, that special region around a star where temperatures might allow liquid water to exist on a planet's surface. 20 to 50%. Let that settle gently into your thoughts. If you go outside on a clear night and look up at the stars scattered across the sky, roughly one in more, every 2 or 3 of those distant suns might host a rocky planet in a temperate orbit. Not necessarily a planet with water or an atmosphere or life. Just a world where the stellar radiation isn't so intense that rock vaporizes, nor so feeble that even carbon dioxide freezes solid. A place where, at least in terms of temperature, conditions might be neither too hot nor too cold. The Kepler mission ended in October 2018 when the spacecraft finally ran out of fuel, but its legacy continues. Scientists are still analyzing the data it collected, making new discoveries years after the telescope itself fell silent. And Kepler's successor, the Transiting Exoplanet Survey Satellite, or TESS, launched in April 2018, continues the search across even wider swaths of sky. Each new exoplanet we discover is more than just another data point in a catalog. Each represents an entire world with its own unique history, its own geology, its own weather patterns, if it has an atmosphere, its own place in the cosmic order. Some of these worlds might be covered in deep oceans. Others might be scorched desert planets where metals rain from cloud decks made of vaporized rock. Still others might be frozen ice balls or gas giants with winds that howl at speeds that would make the most powerful hurricanes on Earth seem gentle by comparison. We can't visit these worlds. The distances are too vast. The journey time's too long for any technology we currently possess. The closest star to our Sun, Proxima Centauri, lies about 4.2 light-years away. Even traveling at the speed of the fastest spacecraft humanity has ever built, the Parker Solar Probe, which has reached speeds of approximately 192 kilometers per second relative to the Sun, the journey to Proxima Centauri would take thousands of years. But we can observe these distant worlds. We can measure their sizes and masses, study their atmospheres, map their orbits. We can learn about their climates and compositions, deduce whether they have moons or rings, determine how old they are and how they formed. And in doing so, we learn not just about those distant systems, but about our own place in the cosmos, about the processes that created the Earth and the other planets in our solar system, about the potential for life beyond our small blue world. The story of exoplanet discovery is a story of patient observation, of careful analysis, of incremental progress building upon itself year after year. It's a story that continues to unfold, with new chapters being written every time a telescope detects another distant world, Every time scientists develop a new technique for characterizing these planets, every time we push the boundaries of what we can observe and understand a little bit further. As we move through this exploration of distant worlds, there's no need to hold every detail in mind. The information will flow without urgency, building gradually, allowing each concept to settle before moving to the next. If you find your attention drifting, that's perfectly fine. The universe has been here for billions of years. These facts and these worlds will remain whether we're fully focused on them or letting our minds wander to other places. We'll journey through several different types of exoplanets. We'll visit worlds so massive they stretch the definition of what we call a planet. We'll explore systems where multiple Earth-sized worlds orbit a single dim star. We'll encounter planets that drift alone through interstellar space, orphaned from any solar system. We'll learn about the methods astronomers use to find these distant realms and how they determine the properties of worlds they can never see directly. Throughout this journey, the pace will remain steady and unhurried. There's a lot to cover, but we have all the time we need. You might choose to listen all the way through, taking in each section as it comes. Or you might let the information wash over you like gentle waves, absorbing what resonates while allowing the rest to simply flow past. Both approaches are equally valid. The universe of exoplanets is vast and varied. It contains surprises that challenged our assumptions and discoveries that open new avenues of investigation. But it's also characterized by patterns and regularities, by physical laws that operate the same way across cosmic distances, by the same forces of gravity and thermodynamics and angular momentum that shape our own world. One thing you'll notice as we progress is that exoplanet science is remarkably young. The first confirmed exoplanet around a sun-like star was discovered in 1995. That's barely more than 3 decades ago. Many of the people reading about exoplanets today were alive before we knew for certain that planets existed around other stars. The field has progressed with remarkable speed, advancing from that single initial detection to the thousands of confirmed worlds we know about today. This youth shows itself in the way scientists talk about exoplanets. There's still a sense of discovery and wonder, a recognition that every new planet reveals something we didn't know before. The vocabulary is still being developed. Terms like hot Jupiter and super Earth and mini Neptune were coined to describe types of planets we never encountered in our own solar system. The very act of categorizing these worlds is an ongoing process, with boundaries that shift as we learn more. What we'll explore in the time ahead isn't meant to be comprehensive. No single journey could cover every confirmed exoplanet or every aspect of exoplanet science. Instead, we'll focus on certain themes and certain types of planets that illuminate broader patterns. We'll visit a few specific systems in detail, using them as examples to understand larger principles. We'll examine the methods that made these discoveries possible, understanding not just what we found, but how we found it. The information flows from the general to the specific and back again. We'll establish broad concepts, then illustrate them with particular examples, then pull back to see how those examples fit into larger patterns. This rhythm allows ideas to sink in naturally without forcing them. Repetition happens, but with different framing each time, approaching familiar concepts from new angles. If you're someone who finds comfort in understanding the scale of things, you'll find that here. We'll talk about distances measured in light years, about planets with masses 10 times that of Earth, about temperatures high enough to vaporize rock and low enough to freeze carbon dioxide into dry ice. But if numbers sometimes feel abstract or difficult to grasp, that's fine too. The specific values matter less than the general patterns they reveal. Similarly, if you prefer concrete details and specific examples, those are woven throughout. We'll visit the TRAPPIST-1 system with its 7 Earth-sized planets. We'll examine hot Jupiters like 51 Pegasi b. We'll explore rogue planets drifting through interstellar space. Each offers its own unique characteristics, its own story of discovery, its own place in the larger narrative of how we've come to understand planetary systems beyond our own. The journey through exoplanet science is also a journey through human ingenuity and patience. Detecting these distant worlds requires instruments of extraordinary precision. It requires telescopes that can measure changes in stellar brightness of less than 1 part in 10,000. It requires spectrographs sensitive enough to detect the tiny Doppler shifts in starlight caused by the gravitational tug of an orbiting planet. It requires observers willing to collect data night after night, year after year, building up the observations needed to confirm that what they're seeing is real. But beyond the technology and the measurements, exoplanet science is fundamentally about expanding our understanding of what's possible. Each new planet discovered is a reminder that the universe contains more variety than we can imagine from our single example of the solar system. Each unusual world challenges us to think more broadly about planetary formation and evolution. Each potentially habitable planet raises questions about the prevalence of life in the cosmos. As we continue, you might notice that certain themes recur. The theme of distance and the challenges it creates for observation and study. The theme of diversity, as we encounter worlds that bear little resemblance to anything in our own solar system. The theme of time, both the billions of years over which these planetary systems formed and evolved, and the mere decades during which we've been discovering them. The theme of scale, from planets smaller than Earth to gas giants many times the mass of Jupiter. These themes interweave throughout the exploration ahead. They're not separate topics, but different aspects of the same larger story about planets, stars, gravity, and the processes that create and shape worlds. Understanding one aspect helps illuminate others, creating a gradually more complete picture of how planetary systems work. So settle in, let your breathing slow. The information will continue to flow at its own pace, without rushing, without pressure. Whether you absorb every word or drift in and out of focus, whether you finish this entire journey in one sitting or return to it across multiple sessions, the content remains the same. These are facts about distant worlds, delivered gently, without urgency, in the hope that they might spark wonder or curiosity, or simply provide a calm backdrop for rest and relaxation. For most of human history, the question of whether planets existed around other stars remained purely speculative. Ancient Greek philosophers debated the possibility of other worlds. Medieval scholars wondered if the stars might be suns with their own retinues of planets. But without any method to detect such distant bodies, the question remained philosophical rather than scientific. The invention of the telescope in the early 17th century began to change our relationship with the night sky. Galileo Galilei turned his improved telescope toward the heavens in 1609 and discovered the 4 largest moons of Jupiter, now called the Galilean moons, in his honor. This observation provided evidence that not everything in the sky orbited Earth, supporting the Copernican model of the solar system with the Sun at its center. Over the following centuries, astronomers discovered more moons, mapped the surfaces of Mars and Venus, identified asteroids and comets. They measured the distances to stars, determined that our Sun is just one star among billions in the Milky Way galaxy, and observed that some stars are actually binary systems where 2 stars orbit their common center of mass. But detecting planets around other stars remained beyond reach. The challenge is one of overwhelming disparity. Stars are luminous. They shine with their own light, generated by nuclear fusion in their cores. Planets, by contrast, shine only by reflected starlight. A planet like Earth reflects only a tiny fraction of the light that falls on it. From the perspective of a distant observer, that planet would be lost in the glare of its parent star, like a firefly next to a searchlight. The difficulty goes beyond mere brightness. Even if you could block out the light of the star, the planet would be incredibly small and faint. From a distance of, say, 10 light-years, Earth and the Sun would appear to be separated by an angle smaller than 1 arcsecond. For comparison, 1 arcsecond is about the angle subtended by a quarter, viewed from a distance of 5 kilometers. Resolving objects separated by such tiny angles requires either enormous telescopes or space-based observations above Earth's blurring atmosphere. These challenges didn't prevent astronomers from trying. Throughout the 20th century, various claims of exoplanet detections were made and later retracted. The first confirmed discovery actually came not around a normal star like the Sun, but around a pulsar, the rapidly rotating remnant of a massive star that exploded as a supernova. In 1992, astronomers Alexander Wolszczan and Dale Frail announced the discovery of 2 planets orbiting the pulsar PSRB 1257+12, located about 2,300 light-years from Earth in the constellation Virgo. They detected these planets through careful timing of the pulsar's radio emissions. Pulsars spin with remarkable regularity, emitting beams of radio waves that sweep across space like lighthouse beacons. Any planet orbiting the pulsar causes tiny variations in the arrival time of these radio pulses due to the gravitational interaction between the pulsar and the planet. The discovery was remarkable, but these pulsar planets existed in an extreme environment. Pulsars emit intense radiation and powerful magnetic fields. Any planets that survived the supernova explosion that created the pulsar would be bombarded by this radiation. These were exotic worlds, fascinating in their own right, but they didn't answer the question of whether planets existed around normal stars like the Sun. That answer came 3 years later. Michel Mayor and Didier Queloz, working at the Haute-Provence Observatory in France, had been using a technique called the radial velocity method to search for planets around Sun-like stars. The method works by detecting the tiny motion of a star caused by the gravitational tug of an orbiting planet. When we typically think about a planet orbiting a star, we imagine the planet moving while the star remains stationary. But this isn't quite accurate. Both the star and the planet orbit their common center of mass, called the barycenter. For a system like the Sun and Jupiter, the Yaowen barycenter is actually located just outside the Sun's surface. The Sun moves in a small orbit around this point in response to Jupiter's gravitational influence. This movement is tiny compared to the planet's motion, but it's measurable. When the star moves toward Earth, its light shifts slightly toward the blue end of the spectrum due to the Doppler effect, the same phenomenon that makes the pitch of a siren change as an emergency vehicle approaches and then passes by. When the star moves away from Earth, its light shifts slightly toward the red end of the spectrum. By carefully measuring these Doppler shifts in a star's spectrum, astronomers can detect the star's motion and infer the presence of an orbiting planet. The technique requires extraordinarily precise measurements. The radial velocity of the Sun, caused by Jupiter, is only about 12 meters per second. For Earth, it's just 9 centimeters per second. Detecting such small velocities requires spectrographs capable of measuring wavelength shifts of 1 part in 10 million or better. Mayer and Queloz had been observing the star 51 Pegasi for months when they noticed a periodic signal in its radial velocity. The star was moving toward and away from Earth with a velocity of about 55 meters per second, and the period of this motion was just 4.2 days. They verified the signal through continued observations, then announced their discovery in October 1995. The planet, designated 51 Pegasi b following the naming convention where lowercase letters starting with B denote planets in order of discovery, had a minimum mass about half that of Jupiter. Its orbital period of 4.2 days meant it orbited its star at a distance of just over 7 million kilometers, roughly 1/20th the distance between the Sun and Mercury. The astronomical community reacted with a mixture of excitement and skepticism. Some questioned whether the signal really came from a planet rather than pulsations in the star itself or some instrumental artifact, but within months, other teams confirmed the discovery using different telescopes and instruments. Moreover, other hot Jupiter planets began to be discovered around other stars, establishing that 51 Pegasi b wasn't an anomaly, but rather the first example of a common type of exoplanet. The discovery marked the beginning of the modern era of exoplanet science. Within a year, several more planets had been confirmed around Sun-like stars. The radial velocity technique began to reveal a diversity of planetary systems that challenged existing theories of planet formation. Astronomers found planets in highly elliptical orbits, planets with masses several times that of Jupiter, planets orbiting binary star systems. Each discovery raised new questions. How did these massive planets end up so close to their stars? Could smaller, Earth-like planets exist in these systems alongside the giant worlds? What did the variety of exoplanetary systems tell us about how common our own solar system's architecture might be? The pace of discovery accelerated throughout the late 1990s and early 2000s. By 2000, approximately 30 exoplanets had been confirmed. By 2005, that number had grown to about 150. The radial velocity method remained the primary detection technique, but other methods were being developed and refined. One particularly promising approach was the transit method. If a planet's orbital plane is oriented such that it passes directly in front of its star as seen from Earth, the planet will block a small fraction of the star's light during each orbit. By monitoring the brightness of many stars and looking for these periodic dimmings, astronomers could potentially detect planets. The transit method had several advantages. Unlike radial velocity, which primarily reveals a planet's mass and orbital period, transit observations could also determine a planet's size. This was crucial for understanding planetary composition. A planet with the mass of Earth, but the radius of Jupiter, would clearly have a very different composition than a planet with both the mass and radius of Earth. Moreover, during a transit, some starlight passes through the planet's atmosphere, if the planet has one. Different atmospheric gases absorb light at different wavelengths, imprinting a characteristic spectrum on the starlight. By comparing the star's spectrum during a transit with its spectrum when the planet isn't transiting, astronomers could potentially identify the gases present in the planet's atmosphere. The first exoplanet discovered to transit its star was HD 209,458b, confirmed in late 1999. The planet had already been detected through radial velocity measurements, but two teams independently observed it, transiting its star, watching the star's brightness dim by about 1.7% for about 3 hours as the planet passed in front. This transit depth, combined with the planet's known mass from radial velocity observations, confirmed that HD 209458b was indeed a gas giant similar to Jupiter. But detecting transits required monitoring many stars continuously. From Earth's surface, this was challenging. Atmospheric turbulence blurs the images, clouds can block observations, and the day-night cycle limits the duration of continuous monitoring. What was really needed was a space-based telescope that could stare at a large number of stars continuously for months or years without interruption. That telescope would eventually become Kepler, but its development took time. In the meantime, ground-based transit searches made steady progress. Smaller surveys discovered a handful of transiting exoplanets. Each discovery refined the technique and demonstrated the potential of the transit method to revolutionize exoplanet science. By the mid-2000s, the field had evolved from the initial excitement of confirming that exoplanets exist to the more methodical work of cataloging and characterizing them. Astronomers were beginning to discern patterns in the data, noticing correlations between stellar properties and the types of planets found orbiting them, mapping out the distribution of planetary masses and orbital periods. The diversity was striking. Hot Jupiters were common enough that they couldn't be dismissed as rare anomalies, yet different enough from anything in our solar system that they demanded explanation. Some planets had orbits so eccentric they couldn't have formed where they currently exist. Some orbited their stars in the opposite direction from the star's rotation, suggesting violent dynamical histories. At the same time, the first hints were emerging that smaller, rocky planets might be common. While the radial velocity and transit methods were most sensitive to large planets orbiting close to their stars, the hot Jupiters that dominated the early discoveries, refined instruments, and longer observation baselines were beginning to detect smaller signals from less massive planets. The stage was set for the next major leap in exoplanet discovery. The Kepler Space Telescope, approved for development in 2001 and launched in March 2009, would transform the field from a catalogue of hundreds of mostly giant planets to a census of thousands of worlds spanning a vast range of sizes and orbital configurations. It would reveal that small, rocky planets are not just possible, but common, and it would provide the statistical foundation for estimating how many potentially habitable worlds exist in our galaxy. But before we explore Kepler's discoveries, it's worth pausing to appreciate how far the field had come in just 15 years. From 0 confirmed exoplanets around Sun-like stars in 1994 to more than 300 by 2009. From theoretical speculation about whether planets might exist to detailed observations of their masses, sizes, orbital parameters, and in some cases even their atmospheric compositions. From wondering if our solar system was unique to recognizing that planetary systems are common and diverse almost beyond imagination. The journey of exoplanet discovery mirrors the broader arc of scientific progress. It begins with questions that seem unanswerable given current technology. It proceeds through incremental improvements in instruments and techniques, each step building on what came before. It experiences moments of breakthrough when new capabilities open up entirely new areas of investigation. And, throughout, it's driven by curiosity, by the fundamental human desire to understand our place in the cosmos. Finding planets around other stars requires overcoming extraordinary observational challenges. The distances involved are measured in light years, the timescales in years or decades of patient observation, the signals in variations of starlight so subtle they would have been undetectable just a few generations ago. Yet, astronomers have developed several ingenious methods for detecting these distant worlds, each revealing different aspects of the planets they discover. The radial velocity method, which led to the first confirmed exoplanet around a Sun-like star, works by detecting the gravitational wobble that a planet induces in its parent star. Imagine holding one end of a rope with a weight attached to the other end, then swinging the weight in a circle around you. You'll feel a tug pulling your hand outward. To keep the weight moving in a circle, you need to pull back, and in doing so, you'll find that your hand and arm aren't perfectly still. They move slightly in response to the weight's motion. The same thing happens with a star and its planets. The planet orbits the star, but the star also orbits the common center of mass of the system. For Jupiter and the Sun, this center of mass is actually located just outside the Sun's surface, about 746,000 kilometers from the Sun's center. As Jupiter orbits, the Sun traces out a small circle around this point, moving at approximately 12.5 meters per second. This velocity is tiny by everyday standards, about 45 kilometers per hour, a modest speed for a car on a city street, but it's enormous compared to the velocities that can be detected by modern spectrographs. The HARPS instrument, for example, can detect radial velocity changes as small as 1 meter per second, and newer instruments push this sensitivity even further. The detection relies on the Doppler effect. When the star moves toward Earth, the wavelengths of the light it emits are compressed, shifting the entire spectrum slightly toward the blue end. When the star moves away from Earth, the wavelengths are stretched, shifting the spectrum toward the red. By carefully measuring the positions of absorption lines in the star's spectrum and tracking how these positions change over time, astronomers can reconstruct the star's motion. The data appears as a periodic curve, with the star's radial velocity oscillating between positive and negative values as it moves toward and away from Earth. The period of this oscillation corresponds to the planet's orbital period. The amplitude of the oscillation depends on the planet's mass and its distance from the star. More massive planets and planets closer to the star produce larger stellar velocities and thus larger Doppler shifts. However, the radial velocity method has limitations. It's most sensitive to massive planets orbiting close to their stars. The signal from an Earth-mass planet in an Earth-like orbit around a Sun-like star would be only about 9 centimeters per second, right at the edge of what current instruments can detect. Moreover, the method only reveals the component of the star's motion along our line of sight. If the planet's orbit is oriented face-on to us, the star won't move toward or away from Earth at all, and the planet will be undetectable by this method. The transit method offers a complementary approach. When a planet passes directly in front of its star from our perspective, it blocks a small fraction of the star's light. For a Jupiter-sized planet transiting a Sun-sized star, the dimming is about 1%. For an Earth-sized planet, the dimming is only about 0.008%, or 80 parts per million. Detecting such small changes in brightness requires high photometric precision and continuous monitoring. Ground-based transit surveys typically achieve precision of about 1%, suitable for detecting hot Jupiters but not smaller planets. Space-based missions like Kepler can achieve much better precision, around 20 parts per million for bright stars, enabling the detection of Earth-sized planets. The transit method provides different information than radial velocity. The depth of the transit, how much the star's brightness decreases, depends on the ratio of the planet's radius to the star's radius. Combined with knowledge of the star's size, this allows astronomers to determine the planet's actual radius. The duration of the transit, along with the planet's orbital period, provides information about the orbit's size and shape. When transit observations are combined with radial velocity measurements, astronomers can determine both the planet's mass and its radius. This enables calculation of the planet's average density, which provides crucial constraints on its composition. A planet with the density of iron must be primarily rocky. A planet with a density closer to water might be an ocean world. A planet with very low density must be a gas giant with a thick atmosphere. Kepler, launched in March 2009, revolutionized transit detection. The spacecraft carried a photometer designed to monitor the brightness of more than 150,000 stars simultaneously. It focused on a single patch of sky in the constellations Cygnus and Lyra, staring continuously at this region for more than 4 years. The mission's observing strategy was based on a simple statistical calculation. Only a small fraction of planetary systems will be oriented such that planets transit their star as seen from Earth. For an Earth-like planet orbiting a Sun-like star, the probability of seeing transits is about 0.5%. To find large numbers of transiting Earth-sized planets, Kepler needed to monitor many stars. The spacecraft's detectors were extraordinarily sensitive. They could measure brightness changes of 20 parts per million or better for stars brighter than magnitude 12. This precision came at a cost. The detectors needed to be exquisitely stable, and any spacecraft motion needed to be precisely controlled to keep the stars in exactly the same positions on the detectors. Kepler's pointing stability was maintained by 4 reaction wheels, devices that spin at high speed and can be used to rotate the spacecraft by transferring angular momentum. When one of these wheels failed in July 2012, the spacecraft could still maintain precise pointing. When a second wheel failed in May 2013, the primary mission was no longer possible. But Kepler's data from its 4 years of continuous observation proved extraordinarily rich. By the time the mission ended, it had discovered more than 2,700 confirmed planets and identified thousands more candidates awaiting verification. The data revealed that planets are incredibly common, especially small planets between the size of Earth and Neptune. Statistical analysis of Kepler's results allowed astronomers to estimate how common different types of planets are. They found that about 30% of Sun-like stars have at least one planet larger than Earth but smaller than Neptune, orbiting closer than the equivalent of Mercury's orbit in our solar system. About 5 to 10% of Sun-like stars have planets between half and twice Earth's size, orbiting in the habitable zone where liquid water could potentially exist on the surface. These statistics represent one of Kepler's most important legacies. Before the mission, astronomers didn't know if Earth-like planets were common or rare. Kepler demonstrated conclusively that small, rocky planets are abundant, at least around Sun-like stars. This finding has profound implications for the search for life beyond Earth, suggesting that potentially habitable environments might be widespread throughout the galaxy. The transit method also enables a technique called transit spectroscopy for studying exoplanet atmospheres. During a transit, some of the star's light passes through the thin ring of atmosphere at the planet's edge before reaching Earth. Different gases in the atmosphere absorb light at specific wavelengths, creating a characteristic spectrum. By comparing the star's spectrum during transit with its spectrum when the planet isn't transiting, astronomers can identify which gases are present in the planet's atmosphere. The technique has been used to detect water vapor, carbon dioxide, methane, and other molecules in the atmospheres of hot Jupiter planets, and more recently in the atmospheres of smaller planets. The James Webb Space Telescope, launched in December 2021, has dramatically improved our ability to characterize exoplanet atmospheres through transit spectroscopy. Its large mirror and sensitive infrared instruments can detect atmospheric features in smaller, cooler planets that were beyond the reach of previous telescopes. Direct imaging represents another approach to finding exoplanets. This involves actually taking pictures of planets separated from their parent stars. The challenge is immense. The planet is typically billions of times fainter than the star and appears incredibly close to it in the sky. Overcoming the star's glare requires special instruments called coronagraphs that block the star's light while allowing light from the planet to pass through. Direct imaging works best for young, massive planets orbiting far from their stars. Young planets are still hot from their formation and glow in infrared light. The separation from the star makes it easier to distinguish the planet's light from the star's light. Most directly, imaged planets have masses several times that of Jupiter and orbit tens or hundreds of astronomical units from their stars. While direct imaging has found relatively few planets compared to radial velocity or transit methods, it provides unique information. It can reveal details about the planet's atmosphere through spectroscopy of the planet's light without contamination from the star. It can detect planets in face-on systems that would be invisible to transit and radial velocity methods, and it opens the possibility of studying planets in very wide orbits that would take decades or centuries to transit or complete a full orbit measurable by radial velocity. Gravitational microlensing offers yet another detection method based on Einstein's theory of general relativity. The theory predicts that mass warps spacetime, bending the path of light passing near it. When one star passes almost directly in front of another star as seen from Earth, the foreground star's gravity acts like a lens, magnifying and brightening the background star. If the foreground star has a planet, the planet's gravity creates an additional brief spike in the brightness curve. The duration and shape of this spike depends on the planet's mass and its separation from the star. Microlensing is sensitive to planets at a wide range of orbital distances, including planets in orbits similar to Jupiter's in our solar system. The challenge with microlensing is that the alignments required are rare and unpredictable. Each microlensing event is also unique. Once the alignment is over, it won't repeat. This makes it difficult to do follow-up observations to confirm and characterize detected planets. Despite these challenges, microlensing has discovered dozens of planets and provided unique insights into the population of planets at large orbital distances. Each detection method has its strengths and biases. Radial velocity is most sensitive to massive planets close to their stars. Transit observations can find smaller planets but require the orbital plane to be edge-on to Earth. Direct imaging works for young, massive planets far from their stars. Microlensing can detect planets at any orbital distance, but only works during rare alignment events. Understanding these biases is crucial for interpreting the exoplanet catalog. The early discoveries were dominated by hot Jupiters, not because these planets are the most common type, but because they were the easiest to detect with the techniques available at the time. As instruments improved and observation campaigns lengthened, smaller planets and planets in longer period orbits became detectable, revealing the full diversity of exoplanet populations. The field continues to evolve. New instruments push the sensitivity of radial velocity measurements to lower masses. Transit surveys like TESS scan wider areas of sky, finding planets around brighter stars that are better suited for detailed follow-up studies. Direct imaging instruments achieve higher contrast and smaller inner working angles, enabling detection of smaller planets closer to their stars. Future missions will continue this progression, finding ever smaller, more Earth-like planets in ever more Earth-like orbits. Among the thousands of exoplanets discovered, one category stands out as both remarkably common and completely absent from our own solar system. These are the super-Earths, planets with masses between approximately 2 and 10 times that of Earth, and radii between 1.5 and 4 times Earth's radius. They occupy the size and mass range between the rocky terrestrial planets like Earth and the ice giants like Neptune. The terminology can be somewhat confusing. The term super-Earth refers only to the planet's size and mass, not to any presumed similarity to Earth in terms of composition, temperature, or habitability. A super-Earth could be a rocky world with a thin atmosphere, similar to Earth, but larger. It could be an ocean world covered entirely in deep water. It could be a mini Neptune with a thick hydrogen and helium atmosphere over a smaller rocky or icy core. The term simply indicates that the planet is larger than Earth, but smaller than Neptune. Our solar system lacks any examples of super-Earths. Earth is the largest rocky planet in our system, with a diameter of about 12,742 kilometers. The next size up is Neptune, with a diameter of about 49,244 kilometers, nearly 4 times Earth's diameter and 17 times its mass. There's nothing in between, no intermediate-sized world that might serve as a local example of what super-Earths are like. This absence initially led scientists to wonder if super-Earths might be rare. Perhaps the gap in our solar system reflected something fundamental about how planets form. Maybe certain planet sizes were naturally uncommon. The discovery of exoplanets quickly demolished this idea. Super-Earths turned out to be among the most common types of planets in the galaxy. Kepler data revealed that roughly 30 to 50% of Sun-like stars have at least one super-Earth, and many have several. These planets orbit at a variety of distances from their stars, from very close orbits taking just a few days to complete, out to orbits in the habitable zone where temperatures might allow liquid water on the surface. The abundance of super-Earths raises an obvious question. Why doesn't our solar system have any? Several theories have been proposed. One possibility involves Jupiter's influence during the solar system's formation. Jupiter might have migrated inward through the primordial disk of gas and dust, then migrated back outward due to interactions with Saturn. This migration could have scattered or accreted any super-Earth-sized planets that were forming in the inner solar system. Another possibility is that super-Earths did form in the early solar system, but were lost to later dynamical instabilities or collisions. The inner solar system experienced a period of intense bombardment called the Late Heavy Bombardment around 4 billion years ago. This chaotic period involved large bodies moving through the inner system, potentially leading to ejections or collisions that removed any super-Earths that had formed. A third possibility is simply that planet formation is inherently stochastic. Different stellar systems, even those with similar initial conditions, can end up with very different planetary architectures due to small variations in the timing of planet formation, the distribution of material in the protoplanetary disk, and random gravitational interactions during the early stages of system evolution. Understanding super-Earth compositions presents significant challenges. Unlike planets in our solar system, which we can study with spacecraft missions, measure directly with seismology, or observe in detail from nearby, super-Earths remain distant and difficult to characterize. We can measure their masses through radial velocity observations and their radii through transit observations, but inferring composition from these measurements alone is difficult. A planet's density provides some constraints. Density equals mass divided by volume, so once we know both the mass and radius, we can calculate the average density. A planet with the density of rock, about 5.5 grams per cubic centimeter, similar to Earth, is likely primarily rocky with an iron core. A planet with lower density must contain significant amounts of lighter materials, water ice, methane, or gases like hydrogen and helium. A planet with higher density might have an unusually large iron core or might be compressed to higher density by its own gravity if it's particularly massive. However, multiple compositions can produce the same density. A large rocky planet with a thin atmosphere might have the same average density as a smaller icy planet with a thick hydrogen envelope. Breaking this degeneracy requires additional observations, particularly spectroscopic measurements of the planet's atmosphere. Some super-Earths have been studied in enough detail to constrain their compositions. The planet GJ1214b, for example, has a radius about 2.7 times that of Earth and a mass about 6.5 times Earth's mass. These values give it a density of only about 1.9 grams per cubic centimeter, far lower than rock. The planet likely has substantial amounts of water, possibly with a thick hydrogen envelope, or it could be what's sometimes called a water world, with a deep global ocean surrounding a rocky core. Other super-Earths have densities more consistent with rocky compositions. The planet Kepler-10b, one of the first rocky exoplanets confirmed by Kepler, has a mass about 3.3 times Earth's and a radius about 1.4 times Earth's, giving it a density of about 8.8 grams per cubic centimeter. This high density suggests a planet that is primarily rock and metal, possibly with an unusually large iron core, making up a larger fraction of its mass than Earth's core does. The diversity of super-Earth densities suggests that these planets span a wide range of compositions. Some are primarily rocky, scaled-up versions of Earth and the other terrestrial planets in our solar system. Others have significant water ice or other volatile materials. Still others have thick atmospheres of hydrogen and helium, making them more like miniature versions of Neptune than enlarged versions of Earth. This diversity complicates the question of habitability. A super-Earth in the habitable zone of its star might seem like a promising candidate for life, but its actual habitability depends critically on its composition and atmospheric properties. A rocky super-Earth with a moderate atmosphere could potentially support liquid water on its surface, but a super-Earth with a thick hydrogen atmosphere would likely be too hot and have too high surface pressure to be habitable, regardless of its distance from the star. The transition between rocky super-Earths and mini-Neptunes appears to occur somewhere around 1.5 to 2 Earth radii. Planets smaller than this threshold are likely to be primarily rocky, while planets larger than this threshold are likely to have substantial gaseous envelopes. This transition isn't sharp. There's a range of planet sizes where both rocky and gaseous compositions are possible, but it represents an important dividing line in understanding the super-Earth population. The existence of this transition raises questions about planet formation and evolution. Do rocky cores inevitably capture thick hydrogen envelopes if they form while significant gas is still present in the protoplanetary disk? Can planets lose their hydrogen envelopes over time due to atmospheric escape driven by stellar radiation? How do the answers to these questions depend on factors like the planet's mass, its distance from the star, and the age and activity level of the star? These questions remain active areas of research. Atmospheric studies of super-Earths using transit spectroscopy are beginning to provide answers, but progress is gradual. Most super-Earths are too small, and their atmospheric signals too weak for detailed study with current instruments. The James Webb Space Telescope is beginning to change this, enabling atmospheric core characterization of smaller planets than was previously possible, but even JWST has its limits. Despite the uncertainties about composition and habitability, super-Earths remain objects of intense interest. Their abundance suggests that they represent a common outcome of planet formation. Understanding why our own solar system lacks such planets while they're common elsewhere could illuminate the specific circumstances that led to our system's architecture. And, among the thousands of super-Earths discovered, some likely have the right combination of size, composition, atmosphere, and orbital distance to be truly habitable worlds where life could potentially arise and thrive. The study of super-Earths also illustrates how exoplanet science expands our understanding of planets in general. Before their discovery, our concept of what a rocky planet could be was limited to the examples in our solar system. Super-Earths show that rocky planets can be much larger than Earth, with different internal structures, different atmospheric properties, different geologic and tectonic processes. They demonstrate that the range of possible planetary configurations extends far beyond what we see locally. As we continue to discover and study super-Earths, each new piece of information refines our understanding. Each atmospheric detection reveals something about how these planets' climates work. Each mass and radius measurement adds to the statistical picture of super-Earth compositions. Each system discovered adds to our catalog of planetary architectures, showing the different ways that super-Earths can be arranged in orbital configurations around their host stars. The super-Earth mystery. Why are they so common in the galaxy but absent from our solar system? May never be fully resolved. The stochastic nature of planet formation means that individual systems can differ substantially even when starting from similar conditions. Our solar system may simply represent one outcome among many possible outcomes, no more typical or atypical than any other system. What we can say with confidence is that super-Earths represent a major category of planets in our galaxy. They're probably the most common type of planet around Sun-like stars. They span a wide range of compositions from rocky to gaseous. Some orbit in their stars' habitable zones, and studying them continues to reveal new aspects of how planets form, evolve, and survive over billions of years in their stellar environments. The very first exoplanet discovered around a Sun-like star was 51 Pegasi b, announced in October 1995. With a mass about half that of Jupiter, it orbits its star every 4.2 days at a distance of just over 7 million kilometers. This represented something completely unexpected. Planets the size of Jupiter were thought to form far from their stars, beyond the frost line where volatile compounds freeze into ice, not in close, scorching orbits where temperatures exceed 1,000 degrees Celsius. These close-orbiting giant planets came to be called hot Jupiters. The name is descriptive. They're Jupiter-sized or larger, and they're hot, with atmospheric temperatures often exceeding 1,500 Kelvin. Their discovery challenged fundamental assumptions about planet formation and forced astronomers to reconsider how planetary systems evolve. In our solar system, the giant planets Jupiter, Saturn, Uranus, and Neptune all orbit far from the Sun. Jupiter, the closest of the four, orbits at an average distance of about 778 million kilometers, more than 5 times Earth's distance from the Sun. This arrangement made sense according to prevailing theories of planet formation, which predicted that giant planets could only form beyond the frost line. The reasoning was straightforward. Close to a young star, temperatures are too high for volatile compounds like water, methane, and ammonia to freeze. These compounds remain in gaseous form and don't contribute to the solid material available for planet building. Beyond the frost line, these volatiles freeze into ice, increasing the amount of solid material available by a factor of several. This increased solid material allows planet cores to grow larger and faster. Once a core grows to about 10 Earth masses, it becomes massive enough to gravitationally capture large amounts of hydrogen and helium gas from the surrounding protoplanetary disk. This gas accretion continues until either the disk dissipates or the planet becomes massive enough to open a gap in the disk, cutting off its gas supply. The result is a gas giant planet, a small rocky or icy core surrounded by a massive envelope of hydrogen and helium. This process requires the presence of the protoplanetary disk's gas, which typically dissipates within a few million years as the young star's radiation and stellar wind clear away the remaining material. If a planet doesn't grow large enough to capture significant gas within this time frame, it remains as a rocky or icy body rather than becoming a gas giant. Hot Jupiters posed an obvious problem for this formation scenario. At their current orbital distances, temperatures would have been far too high for ice to exist when the planets formed. Without ice, there wouldn't have been enough solid material to build cores massive enough to capture substantial gas envelopes. Yet these planets clearly exist and clearly have the massive gas envelopes characteristic of giant planets. The solution to this puzzle involves planetary migration. The planets don't form where we see them today. Instead, they form farther out where conditions are favorable for giant planet formation, then migrate inward to their current close orbits through interactions with other bodies in the system or with the protoplanetary disk itself. 2 main migration mechanisms have been proposed. The first, called disk migration, involves interactions between the young planet and the gas disk in which it formed. As the planet orbits through the disk, gravitational interactions transfer angular momentum between the planet and the disk material. In most circumstances, this causes the planet to spiral inward toward the star, a process called Type 1 or Type 2 migration, depending on whether the planet has opened a gap in the disk. Type 1 migration occurs for planets not massive enough to clear a gap in the disk. The planet feels gravitational torques from the disk material, both interior and exterior, to its orbit. In general, the outer disk material exerts a stronger torque, causing the planet to lose angular momentum and spiral inward. The migration can be quite rapid. A Jupiter-mass planet might spiral from 5 astronomical units to the inner system in just a few 100,000 years. Type 2 migration occurs for more massive planets that clear gaps in the disk. The planet and disk become locked together, and the planet's migration is governed by the viscous evolution of the disk as material flows inward toward the star. This migration is typically slower than Type 1 migration, but it can still move a planet from the outer system to a close orbit over timescales of a few million years. The second migration mechanism involves gravitational interactions with other planets or with a distant stellar companion. In a system with multiple giant planets, gravitational interactions can pump up the eccentricity of one planet's orbit, causing it to follow a highly elongated path. When the planet swings close to the star at periastron, tidal interactions between the planet and star can circularize the orbit, leaving the planet in a close circular orbit. This high eccentricity migration can explain some of the properties of hot Jupiters that are difficult to understand with disk migration alone. For instance, some hot Jupiters have orbits that are tilted relative to their star's equator, or even orbit in the opposite direction from the star's rotation. Such misaligned and retrograde orbits are hard to produce with disk migration, which tends to align planetary orbits with the star's equator, but they naturally arise from high eccentricity migration driven by gravitational scattering. Recent research suggests that both mechanisms probably operate in different systems or even in the same system at different times. Some hot Jupiters show characteristics consistent with disk migration, while others are better explained by high eccentricity migration. The fraction of hot Jupiters formed by each mechanism remains uncertain and is an active area of investigation. The existence of hot Jupiters has implications for planetary systems in general. If giant planets commonly migrate inward, what happens to any smaller planets that might have formed in the inner system? Numerical simulations suggest that inward migrating giant planets would disrupt or eject most smaller bodies in their path. This might explain why systems with hot Jupiters typically lack other planets in close orbits. The hot Jupiter cleared them out during its migration. However, there are exceptions. Some systems have been found to contain both a hot Jupiter and smaller planets, suggesting more complex migration histories. The WASP-47 system, for instance, contains a hot Jupiter along with a super-Earth and a Neptune-sized planet, challenging the idea that hot Jupiter formation inevitably clears out the inner system. The migration of giant planets also affects the delivery of water and other volatiles to the inner regions of planetary systems. In our solar system, Earth and the other terrestrial planets likely received much of their water from asteroids and comets scattered inward from the outer system, possibly by gravitational interactions with the migrating giant planets. In systems where giant planets migrated all the way to close orbits, this delivery mechanism might not operate, potentially making rocky planets in such systems much drier than Earth. Studying hot Jupiters continues to reveal unexpected details about these extreme worlds. Their atmospheres reach temperatures where many compounds that are solid or liquid on Earth exist as gases. Observations have detected water vapor, carbon monoxide, and other molecules in their atmospheres. Some hot Jupiters have been found to have powerful winds that redistribute heat around the planet, creating complex temperature structures. The most extreme hot Jupiters orbit so close to their stars that their atmospheres are being slowly stripped away, intense stellar radiation heats the upper atmosphere to thousands of degrees, giving atoms and molecules enough energy to escape the planet's gravity. Over time, this atmospheric escape can remove significant amounts of mass, potentially transforming some hot Jupiters into bare rocky cores if the mass loss continues long enough. Hot Jupiters also experience intense tidal forces due to their proximity to their stars. These tidal forces create bulges in the planet's shape and generate internal heating through tidal flexing. For planets in eccentric orbits, the tidal forces vary over the course of each orbit, creating even stronger heating. In some cases, this tidal heating might be strong enough to affect the planet's radius, causing it to be larger than would otherwise be expected for its mass and temperature. The study of hot Jupiters has evolved from initial surprise at their existence to detailed characterization of their properties and understanding of their formation. They remain important objects of study because they're relatively easy to detect and characterize compared to smaller, more distant planets. Their large sizes and short orbital periods make them readily detectable by both transit and radial velocity methods. Their high temperatures make them bright in infrared light, enabling detailed atmospheric studies. Yet hot Jupiters also remind us of how different exoplanetary systems can be from our own solar system. Our giant planets orbit at large distances and have nearly circular orbits. They apparently formed roughly where they are today, without undergoing the dramatic migrations that created hot Jupiters in other systems. Understanding why some systems produce hot Jupiters while others, like ours, don't remains an open question that likely relates to the specific conditions present during planet formation, the masses and distribution of material in the protoplanetary disk, and the particular timing of various stages of planet growth and migration. About 40 light-years from Earth, in the constellation Aquarius, orbits a star unlike our Sun. TRAPPIST-1 is an ultra-cool dwarf, a type of star far smaller and cooler than the Sun. With only about 8% of the Sun's mass and 11% of its radius, TRAPPIST-1 barely qualifies as a star at all. Its surface temperature is about 2400 Kelvin compared to the Sun's 5773 Kelvin, and it emits most of its light in the infrared rather than visible wavelengths. Despite its small size and coolness, or perhaps because of it, TRAPPIST-1 hosts one of the most remarkable planetary systems known. 7 planets orbit this tiny star, all of them roughly Earth-sized, all of them packed into orbits that would fit comfortably within Mercury's orbit around our Sun. The discovery of this system, announced in February 2017, represented a milestone in exoplanet science and immediately became one of the most intensively studied planetary systems beyond our own. The system was discovered using the transit method. Astronomers using the TRAPPIST telescope, a small instrument in Chile designed to search for planets around nearby ultra-cool dwarf stars, detected periodic dips in TRAPPIST-1's brightness, suggesting the presence of several transiting planets. Follow-up observations with other telescopes, including NASA's Spitzer Space Telescope, revealed the full system of 7 planets. The 7 planets, designated TRAPPIST-1b through H, in order of increasing distance from the star, have been characterized in remarkable detail considering their distance from Earth. Their sizes range from about 75 to 113% of Earth's radius. Their masses, determined through analysis of gravitational interactions between the planets that cause slight variations in their transit times, range from about 40 to 140% of Earth's mass. These mass and radius measurements reveal that all 7 planets have densities consistent with rocky compositions. They're not mini-Neptunes with thick, gaseous envelopes, nor are they icy worlds like some of the moons in our outer solar system. They appear to be terrestrial planets, similar in basic composition to Earth Venus, and Mars, just arranged in a much more compact configuration around a much cooler star. The orbits of the TRAPPIST-1 planets are noteworthy. The innermost planet, TRAPPIST-1b, orbits in just 1.5 days at a distance of about 1.7 million kilometers. The outermost planet, TRAPPIST-1a, takes about 20 days to orbit at a distance of about 9.7 million kilometers. For comparison, Mercury orbits the Sun every 88 days at a distance of about 57 million kilometers. All 7 TRAPPIST-1 planets orbit closer to their star than Mercury is to the Sun. Yet despite these close orbits, 3 of the TRAPPIST-1 planets, TRAPPIST-1e, F, and G, orbit within the star's habitable zone. The habitable zone around TRAPPIST-1 is much closer to the star than the habitable zone around the Sun because TRAPPIST-1 is so much cooler. The planets in the habitable zone receive amounts of stellar radiation similar to what Venus, Earth, and Mars receive from the Sun. The compact arrangement of the TRAPPIST-1 system has several interesting consequences. All 7 planets are likely tidally locked to the star, meaning they always present the same face to the star, just as the Moon always presents the same face to Earth. This occurs because tidal forces from the star have synchronized each planet's rotation period with its orbital period. Tidal locking creates a permanent day side and a permanent night side. The day side faces constant stellar radiation and would be much warmer than the night side, which never sees the star. This temperature difference could drive powerful atmospheric circulation if the planets have substantial atmospheres, potentially redistributing heat from the day side to the night side. The habitability of tidally locked planets remains an open question. Early models suggested that the atmosphere of a tidally locked planet might freeze out on the night side, leaving the planet airless. More recent climate models indicate that atmospheric circulation can prevent this freeze-out, at least for planets with substantial atmospheres and certain atmospheric compositions. The planets also likely experience significant tidal heating, particularly if their orbits have even slight eccentricities. Tidal forces from the star deform the planets, and variations in these forces over the course of each orbit generate heat through tidal flexing. For the inner planets, this tidal heating might be substantial, potentially driving volcanic activity or maintaining subsurface oceans even if the surface is frozen. The gravitational interactions between the 7 planets create a complex dynamical system. The planets tug on each other gravitationally, causing their orbits to precess and their transit times to vary in predictable but intricate patterns. These transit timing variations allowed astronomers to measure the planets' masses with remarkable precision, providing the mass and radius measurements needed to estimate their densities. The planets also appear to be in or near a chain of orbital resonances. Orbital resonance occurs when the orbital periods of 2 bodies are related by a ratio of small integers. In the TRAPPIST-1 system, the ratios of orbital periods between adjacent pairs of planets are close to simple fractions like 8:5, 5:3, and 3:2. These resonances likely arose during the planet's formation and migration, with gravitational interactions between the planets locking them into these stable configurations. Characterizing the atmospheres of the TRAPPIST-1 planets is a high priority for exoplanet science. The planets transit their star regularly, providing opportunities for transit spectroscopy. Their small, cool star means that the atmospheric signal during transits is larger relative to the star's brightness than it would be for Earth-sized planets transiting a Sun-like star, making atmospheric detection more feasible. Early observations with the Hubble Space Telescope and other instruments suggested that at least some of the TRAPPIST-1 planets lack thick hydrogen-dominated atmospheres. This is consistent with them being rocky planets rather than mini-Neptunes, but it doesn't tell us whether they have Earth-like atmospheres rich in nitrogen, oxygen, and carbon dioxide, or tenuous atmospheres like Mars, or perhaps no atmosphere at all. The James Webb Space Telescope has begun observing the TRAPPIST-1 planets, with initial results suggesting that TRAPPIST-1b likely has little to no atmosphere. This makes sense given that it's the innermost planet and receives the most intense stellar radiation, which would have stripped away any primordial atmosphere long ago and would prevent any secondary atmosphere from accumulating. The outer planets, particularly those in the habitable zone, remain promising candidates for having retained substantial atmospheres. Whether these atmospheres contain water vapor, carbon dioxide, oxygen, or other gases of interest for habitability is still unknown and awaits further observations. The study of the TRAPPIST-1 system illustrates several important points about exoplanet science. First, it demonstrates that small, cool stars can host multiple rocky planets in compact configurations. About 75% of stars in our galaxy are red dwarfs like TRAPPIST-1, so if such stars commonly host rocky planets, then rocky planets might be extremely abundant in the galaxy. Second, it shows that the habitable zone concept must be applied carefully. The habitable zone around a cool star is much closer to the star than the habitable zone around a hot star. Planets in this zone face different conditions than Earth does, different spectral distributions of stellar light, different tidal effects, likely different patterns of magnetic activity, and stellar flares. Whether such planets can actually support life depends on factors we're still working to understand. Third, the system demonstrates the power of detailed follow-up observations. The initial discovery revealed that the system existed, but subsequent observations with multiple telescopes and instruments provided the mass and radius measurements, atmospheric constraints, orbital dynamics, and other details that make TRAPPIST-1 one of the best characterized multiplanet systems known. The TRAPPIST-1 system will likely remain a focus of exoplanet research for many years. Each new observation refines our understanding of these 7 worlds. Each piece of data about their atmospheres, compositions, and histories adds to the larger picture of how rocky planets form and evolve around cool stars. And the possibility, however uncertain, that one or more of these planets might be habitable or even inhabited makes the system a target of intense interest for astrobiology and the search for life beyond Earth. Standing on the surface of one of the outer TRAPPIST-1 planets, if you could somehow survive the conditions there, the view would be extraordinary. The star would appear much larger in the sky than the Sun does from Earth, glowing a dull red. The other planets would be visible as disks rather than points of light, some appearing larger than the Moon does from Earth. During certain times, you might witness planetary transits, with one planet passing in front of another, creating a kind of double solar eclipse, visible only from worlds in densely packed planetary systems. Whether any living organisms have ever witnessed such a sight from the surface of a TRAPPIST-1 planet remains unknown. But the mere existence of this system, 7 Earth-sized worlds orbiting a single small star, 3 of them in potentially habitable orbits, suggests that the universe contains wonders we're only beginning to discover. Not all planets orbit stars. Some drift through interstellar space, untethered to any stellar system, traveling alone through the darkness between the stars. These free-floating or rogue planets represent one of the most intriguing categories of planetary bodies, challenging our assumptions about what defines a planet and raising questions about the violence and chaos of planetary system formation. The existence of rogue planets was predicted theoretically long before any were detected. Numerical simulations of planetary system formation and evolution showed that gravitational interactions between planets could eject some planets entirely from their birth systems. A close encounter between two giant planets, for instance, could result in one planet being flung onto a highly eccentric orbit or ejected completely while the other settled into a more stable orbit. Detecting rogue planets poses enormous challenges. Unlike planets orbiting stars, rogue planets don't transit their host stars, don't cause measurable radial velocity variations, and don't reflect stellar light in ways we can easily observe. They're cold, dark objects drifting through space, emitting only the faint infrared glow of their residual heat from formation. The primary method for detecting rogue planets is gravitational microlensing. This technique relies on the gravitational lensing effect predicted by Einstein's general relativity. When a massive object passes between Earth and a more distant star, the intervening object's gravity bends the light from the background star, causing the star to temporarily brighten. For a rogue planet, this brightening event is brief, typically lasting only a few hours to a few days, depending on the planet's mass and distance. The exact shape and duration of the brightening curve provides information about the lensing object's mass. Planets produce shorter, weaker brightening events than stars do, allowing astronomers to distinguish planetary mass lenses from stellar mass lenses. The first hints of a population of free-floating planets came from a microlensing survey published in 2011. Astronomers analyzing data from observations of millions of stars toward the galactic bulge found evidence for approximately 10 short-duration microlensing events that appeared to be caused by Jupiter mass objects unbound to any star. Statistical analysis suggested there might be nearly 2 rogue planets for every star in the Milky Way. This number was surprising and sparked considerable debate. If accurate, it would mean hundreds of billions of rogue planets drifting through our galaxy alone. Later studies with larger datasets have suggested lower numbers, perhaps 0.25 free-floating or very wide-orbit planets per main sequence star for Jupiter mass objects. The exact abundance remains uncertain, but it's clear that rogue planets exist and may be relatively common. More recently, in late 2024 and early 2025, astronomers achieved a major breakthrough. They measured both the mass and distance of a rogue planet for the first time. The planet, detected through microlensing, has a mass similar to Saturn's and lies approximately 10,000 light-years from Earth. The measurement was possible because the same microlensing event was observed from 2 different vantage points: Earth-based telescopes and the Gaia Space Telescope, which orbits about 1.5 million kilometers from Earth. The difference in timing of the microlensing event as seen from these 2 locations, called parallax, allowed astronomers to determine the planet's distance. Combined with information about the duration and intensity of the lensing event, this enabled calculation of the planet's mass. The result confirmed that this object is indeed planetary mass, not a brown dwarf or very low-mass star, and provided the first direct measurement of a rogue planet's properties. This Saturn mass rogue planet is particularly interesting because planets of this mass are relatively rare among previously detected free-floating objects, which tend to be either very massive, approaching brown dwarf masses, or very low mass, Earth mass, or smaller. The detection of a Saturn mass rogue planet provides evidence that planets of this intermediate mass can be ejected from their birth systems, likely through gravitational scattering by more massive planets. Rogue planets can originate in 2 ways. They might form in protoplanetary disks around stars like regular planets, then get ejected through gravitational interactions. Alternatively, they might form in isolation, condensing directly from collapsing gas clouds like stars do, but without accumulating enough mass to ignite nuclear fusion in their cores. Objects that form in isolation are sometimes called sub-brown dwarfs to distinguish them from ejected planets. The distinction matters for understanding planet formation processes. If most rogue planets are ejected, it suggests that planetary systems commonly undergo violent dynamical phases that result in planet loss. If most form in isolation, it indicates that planet-like objects can form through star-like processes, down to very low masses. Determining which formation pathway produced a given rogue planet is difficult. In principle, ejected planets might retain moons or rings from their time in a planetary system, while isolated formed objects wouldn't have such features. But detecting moons or rings around rogue planets is currently beyond our capabilities. Some rogue planets have been found to have disks of gas and dust around them, similar to the disks around young stars. One particularly interesting example is the object OTS-44, a young, free-floating planetary mass object with a disk massive enough to potentially form satellites. This object appears to be forming in a manner similar to how stars form, suggesting it's a sub-brown dwarf rather than an ejected planet. Another remarkable recent discovery involves a rogue planet designated CHA1107-7626, located about 620 light-years away. This young object, with a mass 5 to 10 times that of Jupiter, is still actively accreting material from a surrounding disk. Observations detected dramatic bursts of accretion, with the planet consuming material at a rate of about 6 billion metric tons per second during the most intense phases. These accretion bursts are surprising because they mirror phenomena observed in young stars but had never been seen in planetary mass objects before. The discovery suggests that some rogue planets form like stars, building up their mass through accretion from disks rather than being ejected from planetary systems. The existence of rogue planets raises intriguing possibilities and questions. If there are indeed hundreds of billions of rogue planets in our galaxy, they represent a significant reservoir of planetary mass distributed through interstellar space rather than concentrated in stellar systems. Some of these planets might retain substantial heat from their formation, possibly enough to maintain subsurface liquid water through tidal heating or radioactive decay, even without a host star. Could rogue planets harbor life? It seems unlikely for most, given the lack of stellar energy input and the cold conditions in interstellar space. But if a rogue planet had a thick atmosphere to trap internal heat and sufficient radioactive elements or tidal heating to maintain warmth, subsurface oceans might persist for billions of years. Life that originated on such a world or was transported there after ejection from a stellar system might potentially survive in these hidden oceans. The study of rogue planets is poised to advance significantly in the coming years. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will conduct a large-scale microlensing survey specifically designed to detect free-floating planets. The mission is expected to discover hundreds of rogue planets, including potentially Earth mass and smaller objects that are beyond the reach of current surveys. These future detections will help answer fundamental questions about rogue planet demographics. How common are they at different masses? Does the frequency of rogue planets correlate with the properties of stars in their birth environments? What fraction formed in isolation versus being ejected from planetary systems? How many retain satellites or other features from their time in planetary systems? Rogue planets also provide a window into the dynamical history of planetary systems. The detection of a rogue planet with specific properties places constraints on the types of gravitational interactions that could have ejected it. Statistical studies of rogue planet populations can reveal how often planetary systems undergo the kind of dynamical instabilities that lead to planet ejection. The concept of planets drifting alone through space carries a certain poignancy. These are worlds that once might have orbited stars, that might have had siblings in complex planetary systems that might even have been habitable before being cast into the darkness. Their existence reminds us that planetary systems are not always stable, that the gravitational dance of planets around their stars can sometimes end in exile for some of the participants. Yet rogue planets are also survivors. They endured the chaos of their ejection, whether from gravitational scattering or from the breakdown of their formation environment. They continue their journey through the galaxy, traveling through regions of space where stellar light is unimaginably distant and faint. They represent a different kind of planet, defined not by their relationship to a star, but by their journey through the interstellar medium, participants in galactic dynamics on timescales measured in millions or billions of years. One of the most powerful techniques for studying exoplanets doesn't image the planets directly or even measure their masses and sizes. Instead, it analyzes the light that passes through their atmospheres during transits, revealing the chemical composition of air on worlds dozens or hundreds of light years from Earth. This technique, called transit spectroscopy, works because different gases absorb light at specific wavelengths. When a planet transits its star, some of the star's light passes through the thin ring of atmosphere at the planet's limb before reaching Earth. Gases in the atmosphere absorb light at their characteristic wavelengths, creating an absorption spectrum that carries the chemical fingerprint of the atmosphere. The absorption is incredibly subtle. For an Earth-sized planet with an Earth-like atmosphere transiting a Sun-like star, the atmospheric signal is only about 10 parts per million, a tiny fraction of the already small transit depth. Detecting such minute signals requires extremely stable instruments and careful data analysis to remove noise and systematic effects. Despite these challenges, transit spectroscopy has successfully characterized the atmospheres of dozens of exoplanets, mostly hot Jupiters and warm Neptunes where the signals are larger. Water vapor has been detected in multiple exoplanet atmospheres. Carbon dioxide, methane, sodium, potassium, and other molecules and atoms have been identified. The technique has revealed clouds, hazes, and temperature structures in alien atmospheres. The first detection of an atmosphere on an exoplanet came in late 2001 when astronomers using the Hubble Space Telescope observed sodium in the atmosphere of the hot Jupiter HD 209,458b. The detection was based on observations at wavelengths where sodium absorbs light strongly. During transits, the planet appeared slightly larger at these wavelengths than at other wavelengths because the sodium-rich upper atmosphere absorbed light from the star. This early detection demonstrated the viability of transit spectroscopy and opened a new era in exoplanet characterization. Over the following years, additional molecules were detected in exoplanet atmospheres. Water vapor, one of the most sought-after molecules due to its importance for life and climate, was first detected in the atmosphere of an exoplanet in 2007. Water vapor has since been found in many exoplanet atmospheres, from scorching hot Jupiters to cooler Neptune-sized planets. The abundance and distribution of water vapor provides clues about the planet's formation history, as water ice is abundant in the outer regions of protoplanetary disks, but scarce in the hot inner regions. The James Webb Space Telescope, with its large mirror and sensitive infrared instruments, has revolutionized atmospheric studies of exoplanets. Its first exoplanet spectroscopy results, released in 2023, included detection of water vapor, clouds, and evidence of photochemistry in the atmosphere of the hot Jupiter WASP 96b. Since then, Webb has characterized the atmospheres of dozens of exoplanets, pushing to smaller, cooler planets than was previously possible. One particularly significant recent result involves the planet GJ 9827d, a world only about twice Earth's diameter, orbiting a red dwarf star 97 light-years away. Observations with both Hubble and Webb detected water vapor in the planet's atmosphere. More remarkably, Webb's observations suggested that the atmosphere might be predominantly water vapor, making this potentially the first example of a steam world, a planet with an atmosphere composed mainly of water rather than hydrogen, nitrogen, or other gases. GJ 9827d is too hot to be habitable, with a surface temperature around 425 degrees Celsius, similar to Venus. But the detection of a water-rich atmosphere on such a small planet represents a major step toward characterizing the atmospheres of truly Earth-like worlds. It demonstrates that transit spectroscopy can reveal the atmospheric composition of planets approaching Earth's size, at least for the brightest, most favorable targets. The detection of water vapor or other molecules in an exoplanet's atmosphere doesn't immediately tell us whether that molecule is abundant or rare in the atmosphere as a whole. What we observe during transits is primarily the planet's upper atmosphere, where the atmospheric density is low but the geometric path through the atmosphere is long. Molecules that are abundant in the lower atmosphere might not contribute much to the transit spectrum if they don't extend into the upper atmosphere. Interpreting atmospheric spectra requires sophisticated modeling. Astronomers construct model atmospheres with different compositions, temperature structures, and cloud properties, then calculate what transit spectrum each model would produce. By comparing these model spectra to observations, they can constrain which atmospheric compositions and structures are consistent with the data. This process is complicated by degeneracies. Different atmospheric models can sometimes produce similar spectra, making it difficult to uniquely determine the atmosphere's properties. High-altitude clouds or hazes can obscure the spectral features from lower-altitude gases, muting the atmospheric signal. Some molecules have overlapping absorption features, requiring very high-quality data to distinguish them. Despite these challenges, each new atmospheric detection adds to our understanding of exoplanet diversity. The presence or absence of certain molecules provides clues about the planet's temperature, the chemical composition of the material from which it formed, the amount of radiation it receives from its star, and the chemical reactions occurring in its atmosphere. For instance, the detection of methane in an exoplanet's atmosphere suggests cool temperatures and possibly carbon-rich conditions. Carbon monoxide indicates high temperatures or non-equilibrium chemistry. The ratio of carbon to oxygen in the atmosphere can reveal whether the planet formed inside or outside the ice line in its protoplanetary disk. The presence of sulfur-bearing molecules might indicate volcanic activity. As we move toward characterizing the atmospheres of smaller, cooler, potentially habitable planets, the search focuses increasingly on molecules that might indicate the presence of life. On Earth, oxygen and ozone are biosignatures, gases produced primarily by living organisms. In Earth's atmosphere, oxygen is maintained at its current high level by photosynthesis. Without continuous biological production, atmospheric oxygen would be removed by reactions with rocks and would drop to very low levels. Detecting oxygen in the atmosphere of an Earth-like exoplanet would be extremely significant, though not definitive proof of life. Oxygen can also be produced by non-biological processes, particularly the photodissociation of water vapor by stellar ultraviolet light in the upper atmospheres of planets around active stars. Confirming that atmospheric oxygen is biological in origin would require additional evidence, such as the simultaneous presence of other gases like methane that would react away quickly in the presence of oxygen unless continuously replenished. The search for biosignatures represents one of the most exciting frontiers in exoplanet science, but it requires capabilities that stretch current technology to its limits. Detecting oxygen or other biosignature gases in the atmosphere of an Earth-sized planet in the habitable zone of a Sun-like star would require observations with next-generation telescopes specifically designed for this purpose. Several such telescopes are being planned or developed. The Habitable Worlds Observatory, a future NASA mission currently in early planning stages, would be optimized for detecting and characterizing potentially habitable exoplanets. Ground-based, extremely large telescopes with mirrors 30 to 40 meters in diameter will also contribute to atmospheric studies, particularly for planets around nearby stars. While we wait for these next-generation capabilities, current facilities continue to push the boundaries of what's possible. Webb is characterizing smaller and cooler planets than Hubble could study. Ground-based high-resolution spectrographs are detecting molecules in the atmospheres of hot Jupiters with exquisite detail, revealing winds, temperature variations, and chemical gradients. Each atmospheric detection, each new molecule identified, each planet characterized, adds another piece to the puzzle of exoplanet diversity. We're learning that atmospheres can be as varied as the planets themselves, thick or thin, clear or cloudy, dominated by hydrogen or heavier gases, showing signs of active chemistry or relatively inert compositions. The study of exoplanet atmospheres connects to many areas of planetary science. Understanding how atmospheres form and evolve requires knowledge of planet formation, atmospheric chemistry, climate dynamics, and the interactions between planets and their host stars. Each atmosphere we characterize provides a test case for theories developed from studying solar system planets, but applicable across the full range of planetary conditions. And ultimately, the study of atmospheres brings us closer to answering one of the most profound questions in science. Are we alone in the universe? While detecting life through atmospheric spectroscopy would require years of careful observation and analysis to rule out non-biological explanations, the possibility of such a detection drives much of the field's development. Every improvement in our ability to characterize atmospheres, every new molecule detected, every refinement of our techniques brings that possibility closer to reality. In the original Star Wars film, Luke Skywalker watches a double sunset from his home on the desert planet Tatooine, two suns sinking toward the horizon together. For decades, this scene remained purely fictional, a creative flourish in a science fiction story. But in September 2011, astronomers announced the discovery of Kepler-16b, the first confirmed planet orbiting a binary star system where both stars are orbited by the planet. Binary star systems are common in our galaxy. About half of Sun-like stars are part of binary or multiple star systems, where two or more stars orbit their common center of mass. In some binaries, the stars are separated by vast distances, hundreds or thousands of astronomical units, and each star can have its own retinue of planets orbiting it individually. These circumstellar planets orbit just one star of the pair. But Kepler-16b is different. It's a circumbinary planet, orbiting both stars of the binary system from outside their mutual orbit. From the planet's surface, if it had a solid surface to stand on, an observer would indeed see two suns, though the view would be quite different from Tatooine's fictional sunset. Kepler-16b orbits two stars, one similar to the Sun, but smaller and cooler, and one much smaller red dwarf star. The planet itself is a gas giant slightly smaller than Saturn, orbiting the pair of stars every 229 days at a distance of about 0.7 astronomical units. This places it outside the habitable zone of the system, making it too cold to be habitable, even if it were rocky rather than gaseous. The discovery of Kepler-16b was significant because it demonstrated that circumbinary planets could exist and be detected. Theoretical models had suggested that planets could form in circumbinary disks, but there were concerns that the gravitational perturbations from the two stars might disrupt planet formation or destabilize planetary orbits. The detection was made using the transit method, watching for periodic dimmings of the stars as the planet passed in front of them. The transits showed complex patterns because the planet's position relative to Earth changes as the binary stars orbit each other, causing the transit times and depths to vary in intricate but predictable ways. Analyzing these transit timing variations allowed astronomers to determine the planet's orbit with high precision and confirm that it was indeed orbiting both stars rather than just one. Following the discovery of Kepler 16b, additional circumbinary planets were found. Kepler 34b and Kepler 35b, both announced in January 2012, brought the total to 3. These planets, like Kepler 16b, are gas giants orbiting relatively close to their binary stars, near the inner edge of the region where circumbinary orbits are stable. The inner edge of stability for circumbinary planets depends on the properties of the binary stars, their masses, the separation between them, and the eccentricity of their mutual orbit. Planets orbiting too close to the binary would be destabilized by the complex gravitational interactions and would likely be ejected or collide with one of the stars within a relatively short time. Most known circumbinary planets orbit just outside this stability limit, typically at distances 2 to 3 times the separation between the binary stars. This proximity to the stability boundary might not be coincidental. If circumbinary planets form farther out and then migrate inward, they might naturally stop their migration near this boundary where the gravitational torques from the disk change. As of early 2026, about 15 circumbinary planets have been confirmed. Most are gas giants, similar in size to Saturn or Jupiter. Only 2 planetary systems are known to contain multiple circumbinary planets: Kepler 47 with 3 known planets and BEBOP1 with 2. Kepler 47 is particularly interesting because its outermost planet, Kepler 47d, orbits within the system's habitable zone. It's a gas giant, so not itself habitable, but hypothetically a large moon. Orbiting such a planet could potentially have liquid water on its surface if it had the right atmospheric properties to trap enough heat. The BEBOP-1 system was initially designated TOI-1338 based on TESS observations that revealed one circumbinary planet. Follow-up observations using the radial velocity method detected a second planet, making BEBOP-1 the second known multi-planet circumbinary system. The discovery demonstrated that circumbinary systems can host multiple planets in stable configurations, much like planets around single stars can form in multi-planet systems. The existence of circumbinary planets raises questions about their formation and evolution. Do they form in the circumbinary disk through the same processes that create planets around single stars? Or do they form farther out and migrate inward? Do the dynamics of circumbinary planet formation favor certain planet types or masses? Theoretical work suggests that circumbinary planets likely form beyond the ice line in the circumbinary disk, where temperatures are cool enough for volatile ices to exist. This would naturally produce gas giant planets if the icy cores grow large enough to capture significant gas from the disk. The observed predominance of gas giants among circumbinary planets is consistent with this formation scenario. Rocky planets might also exist in circumbinary systems, but they would be harder to detect. Transit signals from Earth-sized planets are small even around single stars, and the complex transit patterns in circumbinary systems make detection more challenging. Radial velocity detection is also difficult because the reflex motion of the binary stars due to a small planet would be tiny compared to their mutual orbital motion. The possibility of habitable circumbinary planets has captured public imagination, partly because of the Star Wars connection. a planet in the habitable zone of a binary star system would experience unique environmental conditions. The amount of radiation received would vary as the two stars orbit each other, potentially creating complex climate patterns. The length of day and night might vary, and the seasonal patterns could be quite different from those on Earth. Tidal effects would also be more complex. A circumbinary planet experiences tides from both stars, and the strength and direction of these tidal forces change as the stars orbit each other. For a planet with substantial oceans, this could create intricate tidal patterns unlike anything on Earth. Whether life could adapt to such conditions is unknown. Life on Earth is adapted to the relatively simple cycle of day and night, created by our planet's rotation, and the regular seasons created by Earth's axial tilt. More complex light and temperature cycles on a circumbinary planet might pose challenges, but they might also create opportunities for unique ecological niches and adaptive strategies. One particularly unusual circumbinary planet deserves mention. The system 2M1510 contains a planet orbiting on a polar orbit. Its orbital plane is perpendicular to the orbital plane of the two brown dwarfs at the system's center. This configuration is very rare and wasn't predicted by standard formation models. Its existence suggests that circumbinary planets can end up in unusual orbital configurations through complex dynamical interactions, perhaps involving a third stellar companion that perturbed the system. The study of circumbinary planets continues to reveal the diversity of planetary system architectures. They demonstrate that planets can form and survive in environments that might seem hostile to planet formation. They show that binary stars don't necessarily prevent planet formation, and in fact might host their own populations of planets with unique characteristics. The formation of planets in circumbinary disks faces unique challenges not present in systems around single stars. The gravitational influence of two stars creates gaps and resonances in the disk that can either enhance or suppress planet formation in different regions. Material in the disk experiences complex orbital dynamics, with some orbits stable and others unstable. The disk itself might be warped or tilted relative to the binary orbital plane, adding further complications. Despite these challenges, observations suggest that circumbinary disks can support planet formation. Young binary star systems have been observed with dusty disks surrounding both stars, and some of these disks show gaps and other structures that might indicate ongoing planet formation. The disk around the binary system GW Orionis, for instance, contains a massive inner ring that appears to be tilted relative to the outer disk, possibly due to the gravitational influence of an unseen circumbinary planet. The long-term stability of circumbinary orbits depends critically on the properties of the binary stars. For planets orbiting close to the binary, even small perturbations can lead to chaotic evolution and eventual ejection or collision. Numerical simulations show that there's a critical distance inside which circumbinary orbits are unstable, typically about 2 to 3 times the separation between the binary stars. Most discovered circumbinary planets orbit just beyond this stability boundary, in a narrow region where orbits are stable, but the gravitational influence of the binary stars is still strong. This concentration of planets near the stability limit might indicate that inward migration of circumbinary planets stops at this boundary, or that planets forming closer in are quickly destabilized and lost. The binary stars themselves evolve over time, and this evolution can affect the planets orbiting them. As stars age, they lose mass through stellar winds. This mass loss causes the binary orbit to expand slightly, which in turn affects the orbits of any circumbinary planets. For planets near the stability boundary, Even small changes in the binary orbit might be enough to destabilize the planetary orbit over long timescales. Some binary systems undergo more dramatic evolution. If one of the stars is massive enough, it will eventually evolve into a red giant, expanding enormously and potentially engulfing any close-in circumbinary planets. The star might then shed its outer layers, creating a planetary nebula before settling down as a white dwarf. Any circumbinary planets that survive this process would orbit a very different stellar system than the one in which they formed. The study of circumbinary planets also connects to the broader question of how common binary stars are in the galaxy. Current estimates suggest that roughly half of all Sun-like stars are in binary or multiple star systems. If circumbinary planets are common around binary stars, then a significant fraction of all exoplanets might be circumbinary, experiencing the unique environmental conditions that come with orbiting two stars. Understanding the population of circumbinary planets requires not just detecting individual planets, but conducting statistical surveys to determine how the frequency of circumbinary planets varies with stellar properties. Do more widely separated binaries host planets more or less often than close binaries? Does the mass ratio between the two stars affect planet formation? How does the eccentricity of the binary orbit influence the likelihood of planet formation? These questions remain partially answered. The sample of known circumbinary planets is still small, limiting the statistical conclusions that can be drawn. As more circumbinary planets are discovered, patterns will emerge that constrain models of circumbinary planet formation and evolution. As detection techniques improve and survey programs, like TESS, continue to monitor bright stars across the sky, more circumbinary planets will likely be discovered. Some might be smaller, rocky planets that represent the first examples of potentially habitable circumbinary worlds. Some might orbit in configurations even more unusual than those already known, challenging our understanding of orbital dynamics and stability. Future space missions might specifically target circumbinary planets. A dedicated transit survey focusing on nearby binary stars could find many more examples, particularly of smaller planets that are difficult to detect in current surveys. Direct imaging of young circumbinary planets would provide insights into how these planets look and evolve during their early history. The connection to Star Wars ensures that circumbinary planets capture public attention in ways that many astronomical discoveries do not. But beyond the cultural resonance, these planets represent important tests of planet formation theory and provide examples of planetary environments that differ in fundamental ways from anything in our solar system. They remind us that planets and the stellar systems that host them come in varieties more diverse than we once imagined. Each circumbinary planet discovered adds to our catalog of exotic worlds and exotic orbits. Each measurement of a circumbinary planet's mass, radius, or atmospheric composition provides another data point for understanding how planets behave in these unusual environments. And each theoretical study of circumbinary planet formation and evolution brings us closer to understanding the full range of ways that planets can come into being and persist over cosmic time. We've journeyed through various aspects of the exoplanet universe, from the initial discoveries that confirmed planets exist around other stars, through the methods astronomers use to find these distant worlds, to detailed explorations of different types of planets and planetary systems. Super-Earths common elsewhere, but absent from our system. Hot Jupiters migrating inward from distant formation locations. The seven-world TRAPPIST, one system with 3 planets in the habitable zone. Rogue planets drifting alone through interstellar space. Atmospheric studies, revealing the chemical composition of alien air. Circumbinary planets orbiting twin suns. Each of these topics could fill volumes. Each planet discovered has its own unique story, its own particular combination of mass, radius, composition, orbital characteristics, and history. The 6,000 confirmed exoplanets represent thousands of individual data points, thousands of separate discoveries, thousands of observations and calculations and models and interpretations. Yet underlying this diversity are patterns and regularities. The same physical laws govern all planetary systems. Gravity works the same way around distant stars as it does in our solar system. The processes of planet formation, the accumulation of solid material, the capture of gas, the clearing of protoplanetary disks, operate according to the same principles everywhere. The same equations describe atmospheric dynamics, tidal interactions, orbital mechanics across all these different worlds. Understanding this combination of diversity and unity is part of what makes exoplanet science compelling. Each new discovery shows us something unexpected, some configuration or characteristic that challenges existing models. But each discovery also fits into a larger framework of understanding about how planets form, evolve, and interact with their stars and with each other. The timescales involved in planetary processes stretch from fractions of a second to billions of years. A hot Jupiter, orbiting in 4 days, experiences thousands of orbits every Earth decade, its atmosphere constantly bombarded by stellar radiation, its internal structure slowly adjusting to the intense tidal forces. A rogue planet drifting through interstellar space might not interact with another object for millions of years, cooling slowly in the darkness, its surface gradually freezing as the last heat from formation radiates away into space. Yet both timescales are relevant to understanding exoplanets. The rapid changes on hot Jupiters reveal atmospheric dynamics and tidal physics. The slow evolution of rogue planets illuminates the long-term fate of ejected worlds and the thermal evolution of isolated bodies. Between these extremes lie countless other timescales: the months or years it takes for a planet to orbit its star, the thousands of years for planetary climates to adjust to changes in orbital parameters, the millions of years for planets to migrate through protoplanetary disks, the billions of years for stellar evolution to transform the environments in which planets exist. This range of timescales presents challenges for understanding exoplanets. We observe planets in brief snapshots, seeing them as they are now, not as they were when they formed or as they will be billions of years in the future. Yet we want to understand their full life cycles, from formation in protoplanetary disks through billions of years of evolution in mature planetary systems and potentially to final states around dying stars. Bridging this gap requires combining observations of many different systems at different evolutionary stages. By observing young planetary systems just a few million years old, we see planets in their formative phase, still embedded in disks or freshly emerged from them. By studying systems of various intermediate ages, we trace how planets evolve over time. By examining planets around old stars, we glimpse what the ultimate fate of planetary systems might be. The spatial scales involved are equally vast. The smallest exoplanets discovered are only about the size of Mars, with diameters around 6,800 kilometers. The largest are several times Jupiter's diameter, exceeding 140,000 kilometers across. Planet densities range from less than that of styrofoam to more than that of iron. Orbital distances span from just a few stellar radii out to hundreds of astronomical units. These scales matter because they determine the physical conditions planets experience. A planet orbiting one stellar radius from its star experiences irradiation millions of times more intense than Earth receives from the Sun. Its surface might be molten, its atmosphere might be boiling off into space, tidal forces might be tearing it apart. A planet orbiting hundreds of astronomical units from its star receives almost no energy from the star, relying entirely on its own internal heat for any warmth it possesses. Between these extremes lie the planets in habitable zones, receiving just the right amount of stellar energy that liquid water could potentially exist on their surfaces. But the habitable zone concept itself has subtleties and complications. The inner and outer boundaries depend on atmospheric composition and greenhouse effects. The presence of clouds can shift these boundaries. Tidal locking might drastically alter the climate of planets in habitable zones around red dwarf stars. Stellar activity and flares might strip away atmospheres of planets that would otherwise be habitable. Understanding habitability requires not just identifying planets in the right orbital range, but characterizing their entire environments, their atmospheres, their surface conditions, their magnetic fields, the activity levels of their host stars, the presence or absence of other planets that might perturb their orbits over time. This comprehensive understanding remains out of reach for most exoplanets, but is gradually becoming possible for a select few particularly well-suited targets. The pace of discovery shows no signs of slowing. New planets are being confirmed regularly as follow-up observations verify candidates identified in transit surveys. TESS continues to monitor bright stars across both hemispheres, finding planets that are easier to study in detail than those around the faintest stars observed by Kepler. The James Webb Space Telescope characterizes the atmospheres of exoplanets with unprecedented detail and sensitivity. Ground-based observations continue to contribute as well. New instruments like ESPRESSO at the Very Large Telescope push radial velocity precision to new limits, detecting smaller planets and planets in longer period orbits than earlier instruments could find. High-contrast imaging instruments reveal young giant planets in wide orbits around nearby stars. Transit surveys from the ground complement space-based missions, finding planets around bright stars that are particularly suitable for follow-up characterization. The interplay between discovery and characterization drives the field forward. Discovery missions identify thousands of planets, providing the statistical samples needed to understand planet populations. Follow-up observations characterize individual planets in detail, determining their masses, radii, densities, atmospheric compositions, and other properties. Theoretical work interprets these observations, developing and refining models of planet formation, evolution, and interaction with their stellar environments. Future missions will push further. The Nancy Grace Roman Space Telescope will use gravitational microlensing to find planets at larger orbital distances than most transit and radial velocity surveys can detect, filling in gaps in our knowledge about the distribution of planets throughout planetary systems. Ground-based extremely large telescopes will combine large apertures with advanced adaptive optics to directly image planets and characterize their atmospheres. The proposed Habitable Worlds Observatory would search specifically for biosignatures in the atmospheres of Earth-like planets in the habitable zones of nearby Sun-like stars. Each of these future capabilities builds on what came before. The techniques developed for finding and characterizing hot Jupiters are refined to work for smaller planets. The statistical understanding of planet populations gained from large surveys guides the selection of targets for detailed follow-up. The atmospheric models developed for hot, large planets are adapted to work for cooler, smaller worlds, more like Earth. The search for life drives much of this development. While most exoplanets are clearly uninhabitable, too hot, too cold, lacking solid surfaces, bathed in intense radiation, the existence of thousands of planets around other stars makes it seem increasingly plausible that somewhere among them might be worlds where life has arisen. The question of whether we're alone in the universe is ancient, but only in the past few decades has it become a scientific question that can be addressed through observation and experiment. Finding even one example of life beyond Earth would revolutionize biology, demonstrating that life is not confined to our single world, but can arise wherever conditions permit. Finding no signs of life despite extensive searching would suggest that life is rare, that Earth might be unusual in hosting biospheres that can survive and evolve over billions of years. Either answer would be profound. Either outcome would reshape our understanding of our place in the cosmos. And the search for that answer requires first finding the planets where life might exist, then characterizing those planets in enough detail to determine if they're truly habitable, then searching for the subtle spectral signatures that might indicate biological activity. We're still in the early stages of this search. We've confirmed thousands of planets, but that's a tiny fraction of the planets that exist in our galaxy. We've characterized the atmospheres of dozens of planets, but only for the largest and most favorable targets. We haven't yet found a true Earth analog, a planet with Earth's size, mass, and composition, orbiting a sun-like star at Earth's distance with an atmosphere similar to Earth's. Finding such a planet, if it exists, will require instruments not yet built, techniques not yet perfected, analysis methods not yet developed. But the progression is clear. Each generation of instruments finds smaller planets, cooler planets, planets more similar to Earth. Each refinement of techniques enables more detailed characterization, more precise measurements, more comprehensive understanding. The diversity of exoplanets discovered so far suggests that Earth analogs, if they exist, might be uncommon but not vanishingly rare. Statistical extrapolation from Kepler data suggests that perhaps 10 to 20% of Sun-like stars might have Earth-sized planets in the habitable zone. With hundreds of billions of stars in our galaxy, that still implies billions of potentially Earth-like worlds. But size and orbital distance aren't everything. A planet could be Earth-sized and in the habitable zone, yet lack an atmosphere, or have a thick, crushing atmosphere like Venus, or be tidally locked, or orbit a highly active star that bathes it in sterilizing radiation. The fraction of Earth-sized habitable zone, planets that are actually habitable, with temperate climates and liquid water on their surfaces, remains uncertain. This uncertainty is part of what makes the search for Earth analogs scientifically interesting. We don't know how common they are. We don't know what fraction have retained their atmospheres over billions of years. We don't know how planetary magnetic fields, plate tectonics, moon systems, and other factors influence long-term habitability. Each Earth-like planet we find and characterize will help answer these questions. The exoplanet story is fundamentally one of expansion. Expansion of our knowledge as we learn about planetary systems throughout the galaxy. Expansion of our perspective as we recognize that our solar system is one of countless planetary systems with its own particular characteristics, but also with much in common with systems everywhere. Expansion of possibility as we discover worlds we never imagined and environments we never anticipated. That expansion continues. Every year brings new discoveries, new techniques, new understanding. What we know about exoplanets now vastly exceeds what we knew 10 years ago, which in turn vastly exceeded what we knew 20 years ago, when the field was just beginning to mature beyond initial detections. Where we'll be in another 10 or 20 years is difficult to predict with specificity, but the general direction is clear. We'll know about more planets, tens of thousands rather than thousands. We'll understand planet formation better through observing planets at various stages of development. We'll have characterized the atmospheres of many more planets, including progressively smaller and more temperate worlds. We might even have detected biosignatures in one or more exoplanet atmospheres. Though proving those biosignatures are truly biological will require years of careful observation and analysis. The technological progression that enables these advances is itself remarkable. The First confirmed exoplanet around a Sun-like star required spectrographs capable of detecting velocity changes of tens of meters per second. Current instruments detect velocity changes smaller than 1 meter per second. The first transit surveys detected dimming of about 1%. Current space-based missions detect dimming of tens of parts per million. The first direct images of exoplanets required blocking out starlight to a contrast ratio of about 1 million to 1. Current instruments achieve contrast ratios exceeding 1 billion to 1. Each factor of 10 improvement in sensitivity opens new parameter space for discovery and characterization. Each new telescope, each improved detector, each refined analysis technique extends the range of what's observable. Progress comes through incremental improvements accumulating over years and decades, with occasional revolutionary advances when completely new capabilities come online. Through it all, the fundamental motivation remains curiosity. Curiosity about what's out there in the darkness beyond our solar neighborhood. Curiosity about how common planets like Earth might be. Curiosity about whether life has arisen elsewhere. Curiosity about the incredible variety of worlds that exist and the physical processes that create that variety. This curiosity drives the patient work of observation, the careful analysis of data, the development of new instruments and techniques. It motivates the gradual accumulation of knowledge that characterizes scientific progress, the slow building of understanding through countless small steps and occasional major breakthroughs. And it connects us to a long tradition of wondering about what lies beyond our immediate experience. From ancient philosophers speculating about other worlds, to medieval scholars debating the plurality of worlds, to early astronomers turning their telescopes skyward, humans have always wondered if we're alone, if our world is unique, if the universe contains other places like home. Now, for the first time in history, we have the tools to answer some of these questions. We know planets are common. We're learning which types of planets are most common and where they form. We're beginning to characterize their atmospheres and search for signs of life. The answers we find might surprise us, challenge us, inspire us, or disappoint us. But we'll have answers based on observation and measurement rather than speculation and philosophy. That progression from speculation to knowledge, from wondering to knowing, represents one of humanity's most significant accomplishments. The discovery and characterization of exoplanets adds another chapter to the long history of our exploration of the cosmos, extending our understanding from our immediate surroundings to the galaxy as a whole. The human element in this exploration deserves recognition. Behind every discovered planet are teams of astronomers, engineers, data analysts, and support staff. Someone designed the telescope or spectrograph that made the observation possible. Someone maintained the instrument and kept it functioning properly. Someone scheduled the observations and pointed the telescope at the right targets. Someone downloaded and processed the data. Someone analyzed the results and recognized the signal of a planet amid the noise. This collective effort spans institutions and nations. Large projects like Kepler or JWST involve thousands of people working over decades, from initial concept through design, construction, launch, operation, and data analysis. Ground-based observatories host visiting astronomers from around the world, all using shared facilities to pursue their research goals. Theoretical work draws on computations performed on high-performance computing clusters maintained by dedicated staff. The open nature of astronomical research means that discoveries build on one another. Data from completed missions remains available in public archives for anyone to analyze. New techniques developed by one group are adopted and refined by others. Follow-up observations by different teams confirm and expand on initial discoveries. This collaborative, cumulative approach accelerates progress beyond what any individual or single institution could achieve alone. The cosmos contains multitudes. Planets of every description orbit stars of every type throughout our galaxy and beyond. Some of these worlds might be habitable. Some might be inhabited. Most are surely hostile to life as we know it, but they exist nonetheless, each on its own path through space and time, shaped by the same physical laws that govern our own world, but manifesting those laws in ways we're only beginning to understand. We've explored only a small selection of what's known about exoplanets. There are entire categories of planets we haven't discussed. Lava worlds tidally locked to their stars with one side molten and the other frozen, water worlds covered in global oceans kilometers deep, planets with retrograde orbits traveling opposite to their star's rotation, planets in highly eccentric orbits that experience extreme seasonal variations as they swing from close approaches to wide separations from their stars. Each type reveals something new about planetary physics and planetary formation. Each discovered world adds another data point to our growing understanding of how planets work across the full range of possible conditions. Each observation refines our models and theories, sometimes confirming predictions, and sometimes forcing revisions when reality turns out to be more complex or more varied than we anticipated. Think about the sheer distances involved. Light traveling at 300,000 kilometers per second takes years to reach us from even the nearest exoplanet host stars. The photons arriving at our telescopes from TRAPPIST-1 left that system 40 years ago. They've been traveling through the void of space for longer than the modern era of exoplanet discovery has existed. When those photons began their journey, we had not yet detected a single planet around another sun-like star. The light we observe from distant exoplanets is ancient in this sense, carrying information about those systems as they were when the light departed, not as they are now. This temporal displacement is negligible for nearby systems, but becomes more significant for distant ones. When we eventually observe planets hundreds or thousands of light-years away, we'll be seeing them as they were in Earth's past, before recorded history, before human civilization, before our species even existed. This perspective can induce a kind of cosmic vertigo, the recognition that the universe we observe is not the universe as it exists now, but rather a patchwork of light from different eras, all arriving at our telescopes at the same moment but originating at different times. Yet this very property of light allows us to study cosmic history, to observe the universe at different stages of its evolution by looking at objects at different distances. The study of exoplanets continues to accelerate. New discoveries happen regularly, new techniques are developed and deployed, new missions are planned and launched. The field moves forward through the combined efforts of thousands of scientists, engineers, technicians, and support staff working on projects around the world and in space. What drives this effort? Partly practical considerations, careers built on research, funding that needs to be justified through results, institutional prestige tied to discoveries. But beneath these practical motivations lies something deeper and more fundamental: the human urge to explore, to understand, to push beyond the boundaries of known into unknown territory. This urge has driven exploration throughout human history, from ancient navigators crossing oceans to find new lands, to medieval travelers journeying to distant and kingdoms, to modern astronauts venturing beyond Earth's atmosphere. The exploration of exoplanets continues this tradition, extending it beyond our immediate physical reach into realms we can observe only indirectly, through the subtle effects planets have on their stars and the faint signals they produce when their atmospheres are backlit by stellar light. But the fruits of their labor belong to everyone. The knowledge gained from exoplanet research is freely shared through scientific publications, press releases, educational materials, and public outreach. The images, data, and discoveries enter the public domain, available for anyone to explore and appreciate. This democratization of knowledge represents one of science's great gifts to society. The discoveries made by professional astronomers using specialized equipment and techniques become part of our collective understanding of the universe. They inform our art, our literature, our philosophy, our sense of our place in the cosmic order. Consider how the discovery of exoplanets has changed our collective understanding in just 3 decades. In 1994, we could only speculate about whether planets existed around other stars. Today, we know that planets are common, probably ubiquitous. We know they come in types not represented in our solar system. We know that the conditions required for planet formation are met around many different types of stars. This shift from uncertainty to knowledge happened within a single human lifetime. The implications extend beyond astronomy. The knowledge that planets are common throughout the galaxy affects how we think about the distribution of life in the universe. It influences discussions about the potential for interstellar travel or communication with other civilizations. It shapes our appreciation for Earth's place among the countless worlds that exist. That appreciation can take different forms. For some, the multitude of exoplanets emphasizes Earth's ordinariness. We orbit one star among hundreds of billions, and our planet is one of countless planets throughout the galaxy. For others, it emphasizes Earth's uniqueness. The specific combination of conditions that makes Earth habitable might be rare or even unique among all those worlds. Both perspectives have validity. Earth is simultaneously ordinary in being a rocky planet orbiting a main sequence star, and potentially extraordinary in hosting a biosphere that has survived and evolved over billions of years. The tension between these perspectives, between our cosmic ordinariness and our potential uniqueness, drives much of the philosophical and scientific interest in exoplanets. The search for life beyond Earth makes this tension concrete and observable. Finding evidence of life on other worlds would demonstrate that Earth's life is not unique, that biology is a general phenomenon that arises wherever conditions permit. Failing to find such evidence despite extensive searching might suggest that complex life is rare, that the sequence of events leading from a lifeless planet to one hosting a biosphere requires unlikely circumstances. We don't yet know which of these scenarios is correct. The sample size is too small. We've examined carefully only one planet for evidence of life, and that's the planet we inhabit. Extending this examination to other worlds requires capabilities we're only beginning to develop. The technical challenges are formidable. Detecting biosignatures in the atmosphere of an Earth-like exoplanet requires collecting enough photons to build up a spectrum showing the presence of gases like oxygen, ozone, or methane in concentrations that would be difficult to explain without biological activity. For planets orbiting Sun-like stars at Earth-like distances, this requires telescope apertures of several meters and observation times of hundreds of hours. Current facilities can't yet achieve this for truly Earth-like planets, but the progression is clear. Each generation of instruments reaches farther down the mass and radius scale, studies cooler planets, examines atmospheres in more detail. The James Webb Space Telescope can characterize atmospheres of small planets around cool stars. Future facilities will push to Earth-like planets around Sun-like stars. The timeline for these capabilities extends years into the future. The Habitable Worlds Observatory, if approved and funded, wouldn't launch until the 2030s at the earliest. Ground-based extremely large telescopes currently under construction will come online in the late 2020s. Progress requires patience. The patience to build instruments, to collect data, to accumulate the observations needed to make definitive statements about atmospheric composition and potential habitability. This patience is itself valuable. It enforces a certain humility about our capabilities and our knowledge. We cannot simply demand answers from the universe. We must work for them, gradually building up the observations and understanding necessary to address our questions. The slow pace of progress can be frustrating, but it also ensures that conclusions are well-founded, based on solid evidence rather than speculation or wishful thinking. If you found this exploration of exoplanets calming, informative, or thought-provoking, consider sharing it with others who might appreciate it. Consider looking up at the night sky with a new awareness that many of those points of light are stars with their own planets. Consider following the ongoing discoveries as new worlds are found and characterized. The night sky itself appears unchanging on human timescales. The stars occupy the same positions night after night, year after year. But our understanding of what those points of light represent has transformed. Each star is potentially a sun with its own family of planets. Each might host worlds where processes we can barely imagine are playing out. Worlds being shaped by volcanism, by impacts, by weather systems, by the slow grinding of tectonic processes, by the accumulation or loss of atmospheres, perhaps even by the emergence and evolution of life. This transformation of understanding happened quietly through patient observation and careful analysis, rather than through dramatic visible changes in the sky itself. The stars look the same, but our knowledge of what they represent has expanded enormously. This is typical of scientific progress. The world doesn't change, but our understanding of it deepens. Science progresses through sustained effort and attention. Each observation, each measurement, each analysis contributes to the larger enterprise of understanding. The work continues whether any particular person is paying attention or not, but the experience of discovery is richer when it's shared, when the wonder of finding new worlds is appreciated by many rather than few. Thank you for listening, or thank you for your attention, whether complete or partial, whether you followed every word or let the information flow past as a gentle backdrop for rest or relaxation. Thank you for your curiosity about distant worlds and the methods used to study them. The journey of discovery that exoplanet science represents is ongoing. There's no final chapter, no point at which we'll have learned everything there is to know about planets around other stars. Each answer generates new questions. Each technique developed opens new possibilities. Each discovery illuminates previously dark corners while revealing new areas of uncertainty and investigation. This open-ended nature of the scientific enterprise is both its challenge and its beauty. We're not working toward a predetermined endpoint, but rather exploring an ever-expanding frontier of knowledge. The questions we can ask continue to evolve as our capabilities improve. The techniques we can use continue to develop through innovation and refinement. The understanding we build continues to deepen through accumulation of observations and improvement of theoretical models. If you found value in this content, please like this video and subscribe to the channel. These simple actions help the content reach others who might appreciate it and support the creation of future explorations of cosmic topics presented in this same calm, unhurried manner. Your engagement with this content, in whatever form it takes, represents a connection to this larger enterprise of cosmic exploration. By choosing to spend time learning about exoplanets, you participate in the collective human effort to understand our place in the universe. The knowledge doesn't change because you learn about it, but your own understanding expands, and through that expansion, you join the community of people who find meaning and fascination in the study of distant worlds. The universe is vast. Our understanding grows incrementally. Each piece of knowledge gained opens new questions to explore. The journey continues, with new discoveries waiting in the darkness between the stars, new worlds waiting to be found, new understanding waiting to be built from patient observation and careful analysis. May your own journey, through space or through rest, be peaceful and illuminating. And may you carry with you some appreciation for the incredible diversity of worlds that exist beyond our own, each unique, each governed by the same physical laws that shape our experience, each a reminder that we live in a universe far richer and more varied than any single world could capture. The exploration of exoplanets represents humanity at its best: curious, patient, collaborative, building knowledge through shared effort over time. It demonstrates our capacity to extend our awareness beyond immediate sensory experience to contemplate realities we can observe only indirectly. It shows our willingness to invest resources and effort in understanding for its own sake, pursuing knowledge even when practical applications are distant or absent. This quality, the pursuit of understanding as an end in itself, distinguishes humans among Earth's species. We wonder about things that don't immediately affect our survival or reproduction. We ask questions about distant worlds we'll never visit. We invest decades of effort to learn about processes occurring light years away. This capacity for abstract curiosity, for caring about knowledge beyond immediate utility, is part of what makes us human. The exoplanets exist whether we observe them or not. The stars shine whether we look up or not. But by choosing to observe, to study, to understand, we transform those distant points of light from mere visual phenomena into known, characterized worlds. We extend our sphere of knowledge from the immediate vicinity of Earth to the galaxy as a whole. We connect ourselves intellectually to places we can never physically reach. This intellectual connection has value beyond mere information. It changes how we see ourselves and our place in the cosmos. It provides perspective on our own world and our own existence. It reminds us that Earth is one planet among many, orbiting one star among hundreds of billions. It suggests that the conditions necessary for life, while perhaps uncommon, are not unique to our world alone. Thank you for being here. Thank you for exploring these distant realms, if only in thought and imagination. And thank you for your continued interest in the cosmos and our place within it. May the knowledge of these distant worlds bring you peace. May the vastness of space inspire rather than intimidate. And may you rest well knowing that the universe continues its slow unfolding, with or without our attention, but enriched by our curiosity and our persistent effort to understand it.